So let's talk about industrial design. So I was just gardening. I know it's got nothing to do with anything, but I've been gardening all day, and like, yeah, man, I feel like I'm over sweating. I feel like, like I've been gardening all day. Anyway, so if I look like hell, it's only because I've been working hard. So anyway, let's move on and get on to industrial design. So before we get into this, what I want to do is I want to paint you a picture of why we're talking about this. I want you guys to be able to go into a facility that's got some automated systems. I want you to go into a plastics manufacturing. I want you to go into food packaging. I want you to go into a car wash. I want you to go on to a ship. I want you to go on to shipping. I want you to go on to an area that's manufacturing stuff. I want you to be able to go into these places, even into an automotive shop, and see the airlines and stuff there. I want you to be able to look around and recognize the different pneumatic components that are there and understand why they're choosing certain components for different applications. So essentially, we're talking about a whole bunch of pneumatic components that you already know about. I'll throw a couple new ones in, but you already know about this stuff. Learning nothing new as far as components, but we're going to talk about application for those components. It's really important, and it's also important because in the exam I'm going to ask you questions about applications. So when we say, hey, here's a situation here where there's a pneumatic cylinder that's lifting something or opening something or pushing something. Hey, which of these four types of components would go best for that application? So you guys already know about cushioning and why we would use cushioning. That's important as well. If it's going to extend really quickly and hit the end really quickly, you want cushioning on the outside. But if it's going to retract slowly and it's not even going to retract all the way, you don't need cushioning on the rear. If you don't know what cushioning is, go to like the Actuator week, whenever that was. I forget, week 3 when we talked about actuators. Anyway, so moving on, let's talk about all this industrial pneumatic equipment and where we apply it, essentially industrial designing. Now, we're not actually going to be designing anything, but I want you to think of yourself as a designer as you're going through this so that you can imagine, I see why I might want to choose to put that component there as opposed to some other type of pneumatic component that may actually do the exact same thing, although the application is a little bit better. Let's just go on. So essentially, we're going to look at system air preparation. We're going to look at different actuators. Pressure control, big time. Compressors, it'd be pretty cool. We're going to look at a new compressor that we haven't looked at yet. Airline selection, really very important actually. That's something that you're really going to get. I want you guys to look around at these different things. Hold on, I gotta get a call from my mom. Very good then. Okay, bye. Okay, so that was my mom. So yeah, airline selection. Yeah, I want you guys to be able to like go into different places and look for pneumatic airlines, whether it's a fixed line or a flexible line or other kinds of flexible lines that maybe have sheaths and stuff on them. Yeah, and then control type, pneumatics versus electro-pneumatics. So I think there's a slide in here about, hey, which is better? Should we just go with just a pure pneumatic control, or should we throw some electro-pneumatic in there? And why would we do one or the other? Again, it's all about application. And definitely safety systems. Safety systems, we've already talked about, fail-safe designing and different kinds of valves and stuff that we would put into a system to make it safe. So that's the kind of thing we're going to be taking a look at today. Good. So system air preparation. Now, depending on the in the environment, we need more or less kinds of preparation. Now, essentially what's going on is when we see a diamond-shaped thing that looks like this, right, like that is going to be conditioning air. Okay, it's going to be conditioning the air. Now, it's actually going to be filtering the air. It's either removing water from the air or it's removing particulates from the air, but that's an air filter. That symbol is an air filter. So whenever you're looking at a pneumatic schematic, you're going to see that. Now, which one would you use for which application? Well, it depends on the air in the environment. If you're in a really moist environment, you're going to want a separate water separator. If you're in the desert, you're probably not. If you're in Arizona, you're probably not going to need much of a water separator. But all of these things actually have a water valve on the bottom of them because any kind of filter will actually take water out of the air. So you have to keep that in mind. So essentially, this is the symbol here, and you guys have to think about what's going on. Now, the intake breather filter will filter out some of the dust, but much of it actually ends up in the compressor And then from there, it actually leaves the compressor. It actually leaves the compressor. So we have a breather intake filter and then a filter on the outside, or what we call a system filter. And that's going to be on the outside. Let's take a look at that. So we've got a breather over here. Now a breather is pretty simple. It's just some cotton or something in there. We already talked about this stuff, but depending on the application, you want to choose the right kind of filter strainer and the right kind of breather. And they have oil bath breathers as well. So essentially, they're just really oily. They're like a mesh with a lot of oil in them, and they'll really grab a lot of the particulates out of the air. One of the interesting things about that is, I guess interesting is not the right word. The important thing is that you have to actually filter that. I mean, you have to change the filter because they get dirty. And if it's in a really dusty environment, like not just sand in the air, but other dust, like some places just have a lot of dust. Places with a lot of cardboard packaging end up having dust because a lot of the times the cardboard is coming from other places that's just been sitting there and collecting dust, and cardboard itself produces dust. So depending on the environment, you're going to have to actually change that breather filter, and it can get clogged. So make sure you do that, and always look around to think about how much dust is in the environment, and all of that has to be filtered. And again, if it's a really humid environment, you're going to want to put some kind of water separator. That's the symbol for a water separator. Again, it's just a diamond shape. That guy indicates kind of a little pool of water. This is pretty cool. So what's going on here is that we have these traps. Now, we already talked about this in one of the lectures. I just want to say that this system is designed to pull not only just a lot of water, but specifically that's probably in a paint shop. That system there is probably in a paint shop. So not only is it in a really humid environment, it could be just in a really humid environment, but I am suspecting that the application that they're using the air for has to have really dry air, like in a paint shop. You cannot have any air, any water in your air when you're doing a paint gun. So these guys will be traps. So the air will come through here and you can release the water out of these traps. And that is a huge water separator right there. So it has a desiccant in it, which really absorbs a lot of water. And then you've got to actually open that up to filter it out. So you have to regularly service these things or regularly drain the water. You can also get these things with auto drains in them. Do I have an auto drain? I don't have an auto drain, but anyway, yeah, a paint shop is a really good application. Moisture removal. If it shows an auto drain, there's a little triangle that's inside there. That symbol might be on the exam. I actually don't know. So yeah, if there's a little triangle inside that triangle, it's an auto drain. It drains itself. Whenever it gets full, it goes psst, it pisses out air. So you have to actually put something under it to capture the air, or just have a little hose that goes into a bucket or outside somewhere or whatever. So that you have to keep that in mind. Moisture removal. Yeah, sorry, there's an auto drain right there. That's the auto drain right there. So, and you see that little symbol right there. So this is an aftercooler. What's going on here is that's designed specifically to take a lot of water out because it cools it down. And as soon as you cool air down, all the moisture just leaves. So an aftercooler is something we would use for a really damp environment. If you had a paint shop, you might want to put an aftercooler in as well, because then you wouldn't have to go into all of these extensive work. But this is a lot cheaper than an aftercooler. But you might even want to use both. So this, I'd put an aftercooler in a situation where if it was actually really humid in the environment, you want to do that. So here we go. So actuator selection. Sorry, I just looked at the clock. So essentially, you got to think about it when you're designing systems or when you're looking at stuff. You know what? You'll be able to look at a car wash or something, or you'll be go into an environment where you see cylinders in action. And you'll be able to actually, I hope you'll be able to actually say, I think that's this kind of cylinder. That's a single acting. It's probably got a spring return on it because it's a safety system, and you probably want it to retract if the air goes out or whatever. Okay, so let's just talk about some examples. A swing arm in a car wash, okay, extends and holds a spinning brush against a vehicle. You really want to use a pneumatic actuator for this. If you used a motor, it's going to be a problem because motors apply torque. If they're not physically moving, they don't apply torque anymore. Yeah. I mean, you want the swing arm to push against the car and the thing's rotating. You want to continually push against the car. You want to be able to control the force of that push as well. You can only do that with a pneumatic actuator because air is forgivable. Yeah, it's true. Air is forgivable, but an electric motor, I can't have an electric motor move an arm and continue to push that against something, especially something that's kind of moving back and forth a little bit, like the side of a car. So pneumatic actuator is a really good application for applying force to something where it's not actually moving. Or if it is moving, it's moving just a little bit back and forth. It's very forgivable. Air is compressible. Swing arm retracts when the vehicle is gone. The actuator extends slowly and retracts slowly. Okay, obviously going to put metering in here. But you're going to use a pneumatic cylinder for sure. What kind? Well, you want a double acting for sure, because you want to retract it and extend it. Do you want cushioning? No, because it's not going bam or bam. It's not going extension fast or retraction fast. So you need a double actuator. Yeah, linear motion is required. So you need a linear actuator, right? It needs to be controlled, speed and force in both directions. Okay, so yeah, you need a double acting and no cushioning required. Okay, so there you go. So a clamping cylinder extends slowly and holds onto a part in an inspection steel stamping factory. Okay, so good. So holds onto a part, then it fully retracts. Well, it's not going to extend all the way, right? It's not going to extend all the way, but it will retract all the way. And I probably want to retract really pretty quickly. Because if there's a part there, there's a manufacturing, I want this thing out of the way, go back. Out of the way, go back. So it's going to happen quite a bit. What kind of actuator do you want? Well, you got to think about what happens if the power goes out. You might want this guy, right? Because if the power goes out, I want that part to be removable. I don't want it clamped all the time. So if the power goes out or the air goes out, I want it to retract. So if I put a spring extension, if I put a cylinder in there, single acting spring return cylinder, then it will retract if the air goes out. Right? If I put a double acting cylinder in there with this guy, with a spring return DCV, it will still retract if the electricity goes out, but the air stays on. And actually, you know what? The air is probably going to, actually, even just in the lines, in the hoses, in the pipes, there's enough pressurized air in there to run this cylinder enough to get it out of the way so it's not pushing anymore. You don't even need one of those accumulators. It will actually, if the spring takes over, it'll send whatever pressurized air is left in the lines, just a little bit. Plus, there's a whole tank on the compressor. Right? So, but if that even breaks and there's a line somewhere, there'll be enough little pressure that'll actually at least remove the pressure from the clamping pressure. There you go. So if you want this to extend slowly at all or retract slowly, you want to put metering in. But I pretty much want this to clamp and retract, clamp and retract. So I don't want any metering in there. There you go. So as far as the retraction, you probably want to put some cushioning in here, especially if it's retracting really quickly. I didn't put that there, but it's up to you if you're going to be designing. But when you look at a system like that, you might say, that cylinder's retracting really quickly or extending really quickly. There's probably cushioning in there. And then you can talk to your friends like you know what you're talking about. Okay, here we go. Example, actuator type. Okay, what kind of actuator? An inspection hatch on the deck of a cargo vessel is slowly lifted and slowly lowered. Okay, so I definitely need some metering in there for sure. Okay, what am I going to use? Well, I got to think about safety, right? I have to think about safety. So I'm going to put some metering in both directions for sure. I got metering in both directions. Now, what I can do is, this is kind of cool. This is kind of an override thing that is something that you can use if there's no air to the cylinder and you still need to make whatever that thing is move. Now, you got a couple different options. You can do this, or you can do a three position DCV where the center is passing. Although that could be a problem if you want to stop the cylinder in its tracks somewhere. Because if it's passing, that will allow you to physically move the cylinder yourself. But if it's blocked in the middle, which is probably safer for an application like this, because if it's coming down and you want to stop it either fully, somewhere in between fully extension and fully retracted, you probably don't, you want to have it blocked in the middle. So if you're having a 5.3, you want to have the block in the middle. So what I'm saying here is that one of the situations is, how do we solve this that I can physically move that cylinder or lift that hatch myself? Well, if the power goes out, if the air goes out, I can take this ball valve and open it up, and then I can get a couple people to help me lift that latch. because obviously if there's a pneumatic actuator there lifting the latch, it's helping someone lift the latch. It's heavy. But you know what? If I have this override valve, I can just open that, and that allows the air to kind of pass freely on one side and the other. You can actually physically move it, and the cylinder will just move. Right? There's no restriction. The air will slide back and forth. It'll be okay. So now the other thing is that I can put a pilot operated valve here, which is actually you should combine the two. Probably combine the two. Although the problem is when you buy these pilot operated check valves specifically for this application, it'll screw into the cylinder. And if that's true, then you won't be able to use this component. But that's okay. You can get an inline pilot operated check valve and put it after this if you wanted. Or you can even put a ball valve. You can probably even get a screw-in ball valve that just go right there, and then you can screw in. Yeah, no lines. You can screw in directly your pilot operated check valve. So I think that might be okay. So these are some applications. Now, the pilot operated check valve, as you know, is for safety because we talked about that when we went into actuators. No, ancillary equipment, we talked about that. So this is so that if there's a heavy load here, it's for runaway safety. That load cannot push back. If this DCV just stopped, if this line broke and that line broke, or one of these valves just broke and air just leaked out, that cylinder would retract. But this pilot operated check valve will not allow it to retract. If you don't know what I'm talking about, how that works, go back to ancillary equipment and check it out. Pretty cool. Here we go. So actuator type here. Stirring mechanism is used to stir paint on a road painting cart. The operator presses a button to stir it clockwise and another button to stir it counterclockwise. So back and forth and back and forth. Now, there's a pressurized tank. There's a pressurized tank on this cart, okay? There's no electricity, right? But they've pressurized the tank enough so you can stir this back and forth. So what do you want to do? How are you gonna stir something back and forth and back and forth and back and forth with no electricity? Well, you pressurized air, so you get a motor. You get an air motor, and you stick it in here, and you set one button and the other button. Essentially, in this case, you definitely need a 5.3 because you want to be able to stop that motor at some point. Now, you can put a blocked center here or a passing through center here. The motor will kind of slow down slowly, less kind of shock on the motor when you stop it, but the motor is designed to run really slowly anyway because it's just kind of stirring, right? So this is a good application, or if you put a through there, you may be able to actually go and physically turn that motor yourself, especially if you're maybe setting it up or, I don't know, stirring the paint yourself or something. I really don't know. I mean, I'm just making this application up. I've never actually seen one of these. I'm just imagining an application. And how would you get a pneumatic motor to stir paint on a cart when an operator needs to do this? Well, you would do it this way. And it's up to you to choose which center you want for your 5.3 valve. There you go. So here we go. So pressure control. Right. So essentially, we've got one way to control pressure. Maybe there are two. Maybe there are three. The third one doesn't really control pressure very well. It's throttling, and that's not designed to control pressure. It's designed to control flow, and I'll show you that here. So throttle valves, can we use that to control pressure? Technically, there's a pressure drop across a throttle valve, but it really doesn't control pressure. I mean, I can't think of an application where we're controlling pressure, although there's a pressure drop when we use them. It's kind of like a tap, right? Like the tap on your water tap or your garden hose. You're actually controlling the flow rate, but you're not actually controlling the pressure. I mean, if you were to stop, you got your hose sprayer thing, garden hose sprayer thing, and if you let go of it and stop spraying, even if the thing is on a trickle, right? That if you've turned it, rotated it, it's just that the throttle valve itself or the valve, if you've only turned it on a little bit, the pressure in that hose will build up to whatever the system pressure is. So unless there's really flow happening all the time, we can't really control pressure with this, and it's not designed for that. So I'm just trying to give you a kind of a tangible understanding of how that interacts with pressure, but we don't use it to control pressure. So there are two other ways to control pressure. One is we actually go get a pressure control valve. So, or pressure regulator. And it's designed to actually regulate. Now, we talked about that in ancillary equipment. I went in depth in that. So if you want to know how that thing works, go back to that. The other thing is that we can use a pressure relief valve, and we can control a set pressure. So we can say, hey, you know what? I'm going to turn the pressure system, if you turn the system pressure on to 80 PSI, and you had a pressure relief valve on your downstream, say before some actuator, that was set to 75 PSI, it would constantly be venting air. And it would only vent air down to 75 PSI. So any air past that pressure release valve would actually be at 75 PSI. Now, I just asked you, hey, how do we control pressure? That is a way to control pressure. It's very inefficient. But you'll also see that if there's a pressure drop in your system somewhere that you're not expecting, you're like, why, man? I've got the pressure regulator just set to 80, but downstream, like 20 feet down there are some things that are working, but they're only working at 75 PSI. What's going on? It's probably a leak in your system. So leaks also create pressure change. And if it's a controlled leak, yeah, like a pressure release valve, then that's actually controlling pressure. But typically we use this to control pressure like all the time. But in a pinch, we can control overpressure with pressure release valves. So pressure control, 2 cylinders, the same machine, require different pressures. Okay, so if that's true, I'm going to use this. I'm not going to use this guy. I'm going to use this. I'm going to put 2 pressure regulators. Actually, if one works at 80 PSI and the other works at 50, I'm just going to have the system pressure regulator set to 80, and it's going to go to supply the DCV running 1 cylinder. And then I'm going to have that 80 PSI line go over to a pressure regulator that's set to 50 PSI. And then that is going to then drive the DCV to drive the other cylinder. So there you go. If you have 2 different operating pressures that are required, you use 2 different regulators. That's it. So in this case here, this is a pressure release valve. So what's going on here is if this pressure, for some reason, if there's back force here, there's counter force, it's going to generate extra pressure in the system. This will vent if it goes beyond 70 PSI. But the system is designed to run on 60 PSI. Now, this is a kind of a different symbol here. You see that? There's a switch in here. It's a settable switch. It's not a pressure release valve. It's a pressure switch. It's a settable pressure switch. And that is going to control the motor that controls your what's it called? Yeah, the compressor. Okay, and now you have your pressure. So what's going on is there are 2 systems here. You got 50 PSI. The whole system's working on 50 PSI. If you get back pressure, this thing is actually going to actually, I said that's controlling the compressor, but in this case, this is kind of an overpressure situation. Typically, we do use these to control the pressure of the compressor. So when it gets to that pressure, it just shuts the compressor off. It studies the pressure in the tank. It says, okay, I've hit 80 or 100 and whatever it is, the set pressure is, turn the electrical motor off, it turns it off. But in this case, what I'm doing is I'm saying, if there's back pressure here or back pressure here, that's creating extra pressure in the system, I have 2 fail-safes that are going to release. So I could have this guy release, and then I could have some other valve here that had a solenoid on it that would vent air out. Or I could have this guy actually physically vent air out if that didn't work. So a couple different options here. Safety measures can be added, just like I said. Is there another? Yeah. You can have a pressure release valve. Not only a pressure regulator, but a pressure release valve. And that's what this looks like over here. So the symbol over here indicates just the air just goes out to atmosphere. That's a pressure relief valve. So, and that's there. Yeah, there you go. I think this discussion, the pressure goes above 70. Yeah, this is all about if this gets pushed back here. For some reason, sometimes we generate air backwards into a system. Let's take a look at different kinds of compressors and why we would use one over another compressor. So essentially, we got 2 categories of compressors. One is a reciprocating compressor that's going to generate high pressure and low flow rate. And the other is a rotary compressor, right? So it's going to create a high flow rate and it's going to have a low pressure. So if I've got a situation where I'm filling all of these bags, it's a lot of air that I'm filling, but the pressure is ridiculously low. So I'm going to use a dynamic compressor or rotary compressor as opposed to a displacement compressor, because a displacement compressor is designed to give me really high pressure. Dude, these are like 1/10 of a PSI. I mean, all it is just air in there, right? So I'm going to use a dynamic compressor for sure. Packaging machine, food processing plant. Okay, blows a quick burst of air into the opening bag, right? You're definitely going to be using that. Now you're going to be using this guy, but there's also another kind of situation here where I'm saying here, food processing. So in this thing, there's grease and oil and bearings and stuff in there, and there's contaminants inside that. So you know what I'm going to do? I'm going to use a diaphragm. I've always thought the word diaphragm was spelled really weird. Diaphragm. I hate it. I can't remember how to spell it. Okay, so there's a diaphragm compressor. What goes on there is because there's no metal on metal. We have a really clean gas. So that's used in food, medical, scientific, chemical, toxic, or volatile gases. These are really important. You have to understand that these guys are diaphragm compressors, and they're really cool. So they're actually just rubber membranes that are going up and down. Now, they don't have a really high compression. I mean, some of these now are getting up in 50, 60 PSI, but generally, that's diaphragm compressors. There are these double diaphragm compressors. There's a diaphragm here, and then there's a piston, which is pretty cool. But you can get just pure diaphragm or piston diaphragm. The piston diaphragms can go up to 50, 60 PSI. The pure diaphragms, they'll go up to like maybe 20, not very much, because it's rubber's, you know, malleable. I don't know what that word is. Malleable. Thank you. It's malleable, right? So yeah, but these are really good. So they can't produce really high pressure. You get pretty big flow rates out of them because you can make them really large. And they're very, very clean. So we use those for very clean. Now, the other thing is that this is another compressor application, and it's really cool. In this situation, we want really, really low flow rate, but extraordinarily high pressure. What do we do about that? For instance, these guys, like 4,500 PSI, ridiculous. I've done some work with some of these things. This technology, I've designed some of my medical devices with this technology. It's quite remarkable. And what we use is we have a 3-piston compressor. 1, 2, 3. So this guy is got a really fat piston. The next one's got a smaller piston. There's an intercooler in between. In here, you think there'll be, you know what? I don't know. I think it's not an intercooler. I think these are the cooling jets. Like, I mean, I think maybe this is coolant that goes in here, because I know that to actually compress air down to 4,500 PSI, you need to physically remove heat. Yeah, that's how you do it, because it gets really, really, really hot when you compress it that much. So triple piston diaphragm. I mean, triple piston compressor. Cool. So the other thing is that here's a situation here where I've got really high flow rate, but really low pressure. I mean, it's working at 80 PSI, but ultimately, I've got the air that's coming out of here is just venting to atmosphere, right? So what do? I mean, these guys, they use a lot of air. That uses a lot of air. This uses a lot of air. What do I do? How do I deal with that? You know what? I just get a single stage compressor, because I'm only dealing with 80 PSI, but I get a really big compressor, and I make sure that it's got a high cubic feet per minute rate, and it's just got a big tank on it. I mean, really. I mean, ultimately, that's what you're after. So let's take a look at pneumatic lines. So flexible lines and fixed lines. Okay. So this is a situation where there's a swing arm that's pressing, like we talked about, in a car wash, and there's a swing arm, and there's an actuator pulling it and pushing it. As that goes, that actuator moves. It's physically moving, right? And actually, I've got a pneumatic motor on the end of this thing that's spinning a brush, and I've got to move it. How do I get air to a pneumatic motor on an arm that's moving? I use a flexible line. So what's going on here in this car wash is I've got all of these little black hoses are flexible lines. This guy is a pipe. So he's a solid line, right? He's a fixed line, and then these black lines are flexible, and all of these other ones are also flexible lines as well. And I don't know if they're control lines or if they're lines directly for the actuators. Now, these lines up here are solid steel tubes, right? And they're probably stainless because they're working in a very wet environment. Look at that guy. Look at that huge pneumatic motor that's on there. There's a big pneumatic motor on that thing. Not only goes back and forth, but it goes on an angle as well. So we need flexible lines in here. Now, these flexible lines are pretty solid. They're more like hydraulic lines in that they've probably got a metal sheath around on the inside. Although you can have flexible lines like these guys, right? These are flexible lines, and these are just, they don't have a sheath on them because there's nothing there that's really going to be interacting with them. But these lines that are going to the actuators that are moving are they're being out into the environment where the cars are going by, and they could get, hit or wrecked, or something on the car could pull them or hit them or try and cut them. So you want to put you want to get one with a metal sheath around it and then heavy rubber around it. Flexible lines, they're really important. For instance, here's an example of a flexible line. In this case, this is a tool environment where it's actually a tool, and they're using a hose, and that hose is probably got either kind of some nylon line inside the hose to make it a little stronger, or it could be that there's a corrugated metal pipe inside there that goes around. But if anything, it's hard rubber. Now, this guy is just a vacuum system. Or it looks like, yeah, these are these cool little grippers. And this looks like it's working in an environment where it's just picking up little pieces of plastic. So there's no chance that this line is going to get into something that's going to get cut. But this is more of a machine that's operating. It looks like it's like drilling stuff, and you need maybe a more flexible line there. A tougher line. So with your flexible lines, you have to think about what material they're going to be made of. Now, let's talk about rigid lines. Rigid lines are part of any pneumatic system that's part of a facility. Okay, I mean, even certainly in an automotive shop, if it's just like your shop or maybe a two base shop, it may not have rigid lines. But if it's a large automotive shop, each station needs air. So you have your compressor, you have these main pipes that go up to the ceiling, and they go along the ceiling, and they're tied down or bracketed down. And they don't have to be really accurate wherever they go. You just kind of need to get them from A to B. Once you go to B, you drop them down into the environment, and then you can put a flexible line on. And then the automotive mechanic guy can put his tools on there. Or you could be in an application here like what's going on here. This looks like it's some kind of factory or something. And you have all of these rigid lines, and then there are these drops that go down to each machine. You could actually have a hard drop going down with a regulator on it, a hard drop, and then off the hard drop, you could have a flexible line. Now, often we do use flexible lines to connect one machine to a rigid line. Now, it could be, and some of you guys have done plumbing, that if your tap is specifically in a very specific place, and like behind the wall of a bathroom, right, in the shower or whatever, you have to run rigid lines there. But you can do it. You just have to cut them right and make the angles proper and get them right, and you can do that. But it's a little tricky. So what I'm saying is that machines that are a little bit smaller that you just kind of put down and bolt to the floor, or maybe they're not even bolted, right? Like a tire machine in an automotive shop. It needs air going to it, and it'll be a flexible line that's going to it. But if it's a bigger machine and it needs a good supply of air, like a press at a factory or something, it's going to have a rigid line going to it, because someone's going to spend the time to line up that rigid line and make sure that everything's all bolted in and cut to just the right length so that everything fits properly. So it depends on the application, but often we'll have a rigid line going to transmit the air somewhere, and then a short flexible line going to the actual machine from the rigid line. So here's an example here, many other examples. So essentially this guy here, this robot, although that robot's sitting there and it's not going anywhere, somebody put that robot there, there's probably a flexible line going from the solid line over to the robot. Just because when you install the robot, you know, the actual air line drop is maybe a few feet away, maybe 5 or 8 feet away. But that line that you're dropping in between the robot and the rigid line, I think I said the flexible line is a few feet away. The rigid line is dropped and there may be a few feet. You want to put a flexible line in there. You want to put a good solid industrial flexible line in there with a metal sheath on it, almost like a hydraulic line, so that especially if it's working in an environment like, well, the robot, it could drop heavy things on it and stuff. So you have to think about your lines. But if it's an air gun, you just go get like a really flexible line that you would buy that you would see when you go to the mechanic shop and you see them running their air guns. It's just this red line that goes off. But that line is protected as well. You can whack it with a hammer and it's not going to break. So rigid lines, flexible lines. There you go. So safety design. We're going to talk about safety design and then I'm going to let you go. So safety design. Okay. So however you look at it, you're going to be managing breakdowns with equipment. You're going to be dealing with human error. People break down, right? People, we make stupid decisions, right? Yeah, I made lots of them. I almost lost some fingers and some other things. So, I mean, I'm not proud of that. Really, no, it's stupid. You have to be safe. Safety's like number one. It's a huge, huge thing. But we design systems that will manage people not being safe and or machines that just break down. Yeah, so we have to put that into mind. So you have to put fail-safe design for operators and for the machines because everything breaks down. We can do that by putting physical barriers in. We can put electronic and pneumatic lockout systems, right? So if someone puts their hand in there, it just locks it down. Alarm warnings. I mean, that's safety as well, right? Special safety controllers. This is really cool. Now, if you're an electromech, you're actually going to study safety PLCs, like machines specifically designed for safety, and they make safety decisions, and they're like super redundant lockdown safety decisions. Pretty cool. Emergency stops, big deal, really big deal. Like, look around. When you go into lots of different places, look around for those emergency stops. Actually, especially if you're working in a place, even for a day, if you're going into work or work somewhere, or you're a salesman or whatever, look around for the safety system. Look for the fire extinguisher and look for the safety for the power stops, emergency stops. The list goes on and on and on and on and on. It's important. Let's just talk about some safety design here. Okay, one thing is an auxiliary air tank. Now, we did this in lab 6, so you guys are one of the labs, whichever one, the one we did online, where you're studying auxiliary air tank. So we got a reserve tank that allows this thing to still work 1 or 2 times if the compressor goes down. Yeah, so the backup power system here, the reserve tank. So I'm going to set this to 80 psi. My system pressure is 90 psi. And you might see this in a situation where they absolutely need to at least run this thing 1 or 2 times. You know, that example, I think, from the lab was that, you know, there was a ship that's lifting this thing and lowering this hatch. It's important that that hatch is able to lift and lower. So you want to run it at least 1 more time to get it open, or maybe to get it closed, because that's also important too on a ship, because if it's a storm and you're like, oh, the compressor's gone, the power's out, how do we close this thing? There's a safety backup tank that has enough pressure just to close it and open it and close it once, maybe, something like that. So there you go. So safety design stuff is really important. Metering, here we go, runaway loads. In this case, I would put a pilot operated check valve right in there. I put it right in there because this thing's going to run away and go down. So I'm going to put metering in here to slow down my runaway load protection. And I'm also going to put a pilot operated check valve in there. Really very important. So there you go. So pilot operated check valves. Yeah, there you go. It's just seeing whenever you're lifting a heavy thing. So what we've just done is just talked about I just wanted to talk safety stuff with you. I just wanted to talk industrial application. I wanted to talk about why we use certain things in different places. More so, I just wanted to give you a mindset and give you the kind of the desire or the challenge to look around whenever you go anywhere. One, always look for automated systems wherever you are. Just, I know how that works. I know how that works. But specifically when you're looking at pneumatic systems, you may be able to say, I bet you there's that kind of cylinder. I bet you they have that kind of safety system. Anyway, there you go. Yeah, that's it. That's the last discussion of this course. I hope you got a lot out of that, and thank you very much for participating. Yeah, that's all.